Hey there, Islanders. It's Miss Griggs. In this video, I'm going to go over how to complete the Models of a Crystal lab. You're going to need to find the Models of a Crystal handout that looks like this and open up the PowerPoint attached to the assignment on Schoology. All right, so let's have a look at the PowerPoint. So basically what you're going to be doing is you're going to be looking at the 4 different models of a crystal, and I'm going to show you the tennis ball examples as we go over them. So you're going to then sketch the models on the worksheet, and I would include some of the information that's on the slides as well on the worksheet. And then we're going to answer some interpretation questions together. Okay. All right. So the first model that you're going to be looking at is the simple cubic model. Okay, so here is the example of the simple cubic model, and I will pop back up. Right, see? So here is the simple cubic model, and each of the tennis balls represents an atom. All right, so in this crystal, we have 4 atoms on top of 4 atoms. So if I were to draw that, I will show you how I will draw it. Okay, so this is the information that I would include in my drawing. I would draw this model to the best of my ability. That's what that little drawing is. And then I also realized that it's a cube, so it was really easy for me to just draw a cube and then put circles on each of the corners to represent each of the atoms. And I wrote out how many are on each level or layer. So I did 4 units on top of 4 units, and then one of the notes on the PowerPoint said that it had lots of gappiness, and if you look at the model, you can see lots of gaps and space in between each atom. And then because it had lots of gappiness, it also had lots of slip planes, which are the planes on which the atoms can slide past one another. And because it had lots of slip planes, it made it ductile. Okay, let's go back to the PowerPoint. The next atom or next crystal is going to be the face-centered cubic, so FCC, and it looks like this right here. So I have 5 atoms on top in like an X shaped. Then I have 4 atoms in the middle, kind of like like the top of the cubic model, and then 5 more on the bottom. So this one was much more tightly packed compared to the other one. There's not a lot of space in it, so it doesn't have a lot of gappiness, but it does have lots of slip planes. So if I go back to my picture here, you can see that when I drew this one, I just drew 2 cubes, and then I drew like another cube kind of in between it. That one was kind of hard to draw. So that's why I did it like this, where I had 5 units on top of 4 units on top of 5 units. And we said that it has a lot less gappiness, it's more tightly packed, and it had several slip planes. Because it had those slip planes, it makes it less workable. And workability means that you can only manipulate it so far before it seizes up, the material seizes up. Okay, my next example is BCC, so body-centered cubic. And this one is like the first example, the cubic, but instead of having 4 and 4, it has 1 in the middle, kind of sandwiched in between there. And this one is very loose, lots of gappiness more than the cubic example, and lots of slip planes. So you can see that it's got 4 and then just 1 in the middle. And let's go back to my dot cam. So BCC was a lot easier to draw because I drew my cube again right here. I drew my cube, and then I just drew another atom in the middle and connected them all together. And then I also drew how it's stacked 4 units on top of 1 unit on top of 4 units. Basically, it's like a cubic with an atom in the center of it. We have tons of gappiness, lots of slip planes. Because it has lots of slip planes and lots of gappiness, it makes it very ductile and malleable. Ductile means it can be drawn into a wire very easily. Malleable means it can be hammered into sheets very easily. Okay, and my last example is going to be hexagonal closed packed, or HCP. Okay, so hexagonal closed pack, and let me zoom in on this one because this one's kind of neat. So you have 7 atoms on the bottom right here. So it kind of looks like a flower with 1 in the center surrounded by 6. And then in the center, between the 2 7 layers is a layer of 3, which is kind of like in a triangle shaped. And this is how you get the hexagon shape, hexagonal closed packed. This one is a lot less gappy. Has very little gappiness in it. It's very tightly packed, has very few slip planes in it, and that makes it very brittle. Okay, so this isn't typically the type of metal that we would work with that has this HCP structure to it because of its brittle properties. So this one was really kind of hard for me to draw. So I didn't draw my like cubic type model. I just drew how it is stacked on each other. So I had my 7 units on top of 3 units on top of 7 units. It has a lot less gappiness, a lot fewer slip planes, and it is very, very brittle. Okay, so once you've gotten those all drawn in and you've gotten some notes taken on those, you're then going to go and answer these questions, and we're going to answer them together. So question 1 says face-centered cubic FCC and body-centered cubic BCC and HCP, hexagonal closed packed, are types of packing commonly found in material. The one that is not as closely packed of those 3, so which ones of these is not as closely packed? So we have this one here, which is BCC. You can see it's got lots of gappiness. Compared to the FCC, not as much. And then our HCP, which has the least amount of gappiness. So which one has the most? It's going to be this one right here, the BCC, body-centered cubic. Oh, might as well just go ahead and do that. Okay. Question 2 says a precious metal of gold and silver packed together in the manner of model B. So this is model B right here. This was the FCC model where you had 5, 4, 5. Crystalline structure common of gold and silver, and that was face-centered cubic. Question 3 says zinc, which is commonly used in galvanized steel. Galvanized means that you add a layer of zinc to prevent corrosion. So is represented by model D, which one was model D? This was HCP, hexagonal closed packed. All right. Question 4 says manganese has a crystalline structure like that of model A. That's this model here. All right. This structure is not common for metals and is called cubic crystal. And the reason why it's not very common in the metals is because this one is not as easy to use. The most common types of metal crystals are going to be your BCC or your FCC because these are the most workable. All right, guys, so once you've filled in your drawings and your notes on the models and you've filled in your 4 interpretation questions, make sure you submit a PDF or a picture on Schoology of the assignment. If you have any questions, please email me or come to my office hours on Tuesday or Wednesday from 2 to 3:15. Bye, guys.